Cool. This week's paper review is log structured protocols in Delos. Discusses a critical component of Delos, which is Facebook's system, or a Facebook system for storing control plane data like scheduler metadata and configuration. So according to the authors, Delos is replacing a number of systems that store control plane data, like Zookeeper, inside of Facebook. So this is, we talked about it previously, but this paper is just one of several about Delos. Previous paper on the system, Virtual Consensus in Delos, won a Best Paper Award at OSDI 2020. And there are great reviews of that paper from Alexi and Murat in the morning paper. And there's also a great talk from Mahesh, and I'll share the links to those in speaker notes. So the agenda for today is why develop a storage system for control plane data. We're going to talk about what are the paper's contributions, and then the design and implementation, and lastly, an evaluation of the system inside of Facebook. So the motivation, these slides are also generously donated from Mahesh's, or at least the diagrams are generously donated from Mahesh's talk at SOSP. But why develop a storage system for control plane databases? So storage systems for control plane data are placed under different constraints than systems that store application data. For example, control plane systems must be highly available and strive for zero dependencies. And again, control plane data is information like information the scheduler would have, configuration, naming, and sharding. And actually, it's interesting that sharding is mentioned here because there's another Facebook paper that came out about Shard Manager. Yeah, just interesting side note. So at the same time, it's not sufficient to provide a single API, like a simple key value interface for control plane databases, because the system, the data might be stored in a key value store, it might be stored in a SQLite database, and another example would be something like Zookeeper. So normally databases that are trying to store control plane data duplicate many of the same pieces of logic. And so Delos aims to limit duplicate solutions to the problem that are faced by these types of databases. So one of the key insights in the paper and noted by the other Delos papers is that control plane databases can be based on a replicated log. Many systems use log replication to maintain multiple copies of a data set or to increase fault tolerance. Two examples are MySQL replication, which is covered in previous papers from Facebook, like Tau and the Scaling Memcache paper. So consumers of a replicated log, for those who are not familiar with this idea, consumers of a replicated log execute logic on the data that is stored in the log, in log entries, and they produce materialized state or state of the world. And each node that has consumed the log up to the same point will have the same state of the world, assuming that the log consumption code is deterministic. And the name for this type of technique is state machine replication. So there's a problem, which is that many systems that are built on this technique re-implement features, and the solution is to make building blocks that can run on top of the log and make those building blocks reusable, and that's a lot of what the paper talks about. So to enable code reuse, Delos implements common functionality in those building blocks, and those building blocks can run under higher level application-specific code. And the authors called this approach the Stacklike approach, log structured protocols, and they discuss how the technique simplifies the development and deployment of state machine replication systems because of code use and upgradability and the flexibility that this type of implementation provides. So what are the paper's contributions? There are many things talked about in the paper, but the three contributions that stood out to me are the design for log structured protocols, which is discussed or mentioned in the previous slide, the implementation of several log structured protocols and 2 production databases that use the abstraction, and last but not least, there's an evaluation of the system. So I think that might be an off by one error there. But diving a little bit into what are log structured protocols and how do they work. So each log structured protocol has 4 primary components. There's the application logic, which is the unique functionality that often represents the interface between the replicated state machine and an external system. One example of application logic is converting log entries into SQL statements that write to a database table. Another component are engines. So the engines implement common functionality like batching writes to the log or backing up log entries to external storage. And there's more information on the various engines later on in the presentation. Another key component is the local store, which contains the state of the world. So engines and application logic, as you can see on the right, read and write to the local store, which is implemented using RocksDB. That's mentioned in the paper, but they say that, oh, you could have a local storage system that's based on other types of databases. And then last but not least, there's the shared log, which is the lowest level of the stack. And that's operated on by a common base engine that handles reads and writes. So another interesting component of the system is that if you see, we're at the bottom of the figure, there's a header, their header A and B, and those basically engines can add headers similar to what you see in packets, or in TCP/IP, where different layers of the stack will add different information and then unpack it, etc. So it's an interesting idea that is mentioned in the paper. So diving a little bit into the engines, they are a key building block of each log structured protocol, and they allow developers to compose existing functionality and to focus on implementing a small set of custom logic. So each engine interacts with the layers above or below through an API that relies on proposals. So this API has two main calls. There's propose, which is used to send messages down the stack towards the shared log, and apply, which is used by lower level engines to transfer messages up the stack. And while responding to calls, the engines can also read or write to the local store, and that maintains the current state of the system. So additional calls set up the layering in a log structure protocol, coordinate trimming the log. You can also have there's also this method called sync, which requests all entries from a lower level engine. And there's also various hooks. There are also various hooks that allow an engine to respond to events. For example, using a callback that is triggered after the apply function succeeds. So there are more methods that are mentioned in the full paper. So for more context, would recommend checking that part out. So diving into the implementation, the paper talks about 2 databases and 9 engines. So the 2 databases that the paper talks about are Delos table, which is a database that offers a rich API with support for transactions, secondary indexes, and range queries, and also provides strong guarantees on consistency, durability, and availability. And then there's also Delos, which is a zookeeper-like interface that has CRUD operations on a hierarchy of nodes, basically copying or re-implementing zookeeper. So as far as engines, I'm going to talk about a few of them that stood out to me, but the paper goes into more depth on all of the engines, all 9 engines. So I'm going to talk about 3 engines that I thought were interesting. There's the observer engine, the session order engine, and last but not least, the batching engine. So as you can see here, the observer engine is placed between different engines in a Delos stack, and that provides reusable monitoring functionality by, for example, tracking the time spent in a given engine. So you would track the start and end of different events. There's also the session order engine, which implements some of the key ideas in zookeeper sessions, which are unique in how they, I'm not going to dive into this part of the presentation, but zookeeper has this idea of sessions, and the paper points out, oh, the session order engine is an example of being able to implement custom logic and just slide it right in to a stack, and that's a benefit of Delos. So last but not least, there's the batching engine, which groups entries into a single transaction right to the local store. So this approach enables high performance and provides a common implementation that both Delos table and Zelos use. So that's related to one of the design goals. So the valuation section of the paper talks about several things, but what I wanted to focus on was two questions essentially, which is there overhead inherent to the design of Delos and these protocol stacks, log structure protocol stacks? And then does the design facilitate the performance improvements and upgradability that the paper claims should be an outcome of designing this type of system? So when evaluating overhead, the paper considers the apply thread, and that's because the upcall relates to different transitions between each engine. So they're basically checking out, is the design of Delos with multiple layers, does that introduce some overhead? And if so, what is the overhead? And the paper notes that of the CPU consumed in the fleet, apply only makes up 10% of the utilization, meaning that apply isn't adding significant overhead relative to some of the benefits that the Delos log structure protocols add. So the second main category of results is related to the benefits of code reuse. So one example that the paper cites is the introduction of the batching engine that was discussed in the previous section. And the deployment of the batching engine was relatively straightforward. You essentially slide it in to a stack, and then it is able to handle batching fairly seamlessly. And this adding it contributed to a 2x throughput improvement. And the engine could be rolled out to other protocols, not just this. Any new protocol essentially that is built in Delos would be able to theoretically take advantage of the batching engine. So I think that is, one last slide. So what are the benefits of the log structure protocol design? There's the rapid deployment that I mentioned. They were able to start with simpler log structure protocols and then essentially evolve them over time by making incremental upgrades. So building a new engine, for example, that batches writes, sliding it in, making changes to the other engines, which relates to the third benefit, which is code reuse. So you can implement changes in one engine and gradually roll out those changes, and then eventually all protocols that have adopted those, that engine will be able to take advantage of those specific improvements. There's also the ability in log structure protocols to customize behavior. So the paper mentions how in the Zelos implementation, which is based on Zookeeper, Zookeeper has these session ordering guarantees, and the Delos log structure protocol design supports that custom behavior. You implement it in an engine and then slide that engine in. The last benefit that the paper cites, or that Mahesh has talked about, is improved performance. So if you make performance to a common engine, or you implement a new engine that could help with performance, you could theoretically slide that engine in to a different stack, and multiple stacks would be able to benefit. So that, I think, is all that I have. Thanks. Now we can kind of go into some questions.